All right, recording has started, and I'm going to take you, first of all, the exams are graded, and you can take a look at your exam. You can see comments on anything that was marked wrong. Make sure you understand all of your errors, and if you do not understand something, you can talk to one of your classmates. You can send me a message. Uh, but make sure you clarify the issues so that you understand every single problem that you got wrong on the exam. Calculus really works on that basic foundation, so if you got something wrong there, you'll tend to, if you don't clear up that issue, you'll tend to see that same issue pop up again and cause you more difficulties in the next exam and so on. Overall, the exam results were very good though. And I'm going to take you to a practice quiz for today. Before launching into the practice quiz though, let me announce that I'm going to have the spokesperson for each group rotate now. So it's been doing very well with the leader of each group being the spokesperson. And what I'd like to do now is have the leader of each group appoint who is going to be the spokesperson today, and then just get into a rotating scheme. So each day the leader of the group will say, Joe, you're the spokesperson for our group today. You can set up a rotation scheme, or they can just, send a quick little message each day who the spokesperson is. And the first time that I call on somebody in a group, I say, Group 3, what's your answer? The first person that answers for that day, identify yourself by name. Say, this is Alondra, and here's our answer, so on. And then, you'll be the same spokesperson for that group for the rest of that day, so the next times you don't have to say your name each time. But the first time, do that, and that way we'll kind of get more voices in, and we'll get a feel for who everybody is in the whole class, and I'll get that feel. So let's go ahead and do that now. If the spokesperson could go in everybody get into their little chat group. The spokesperson can just say who the group leader can say who the spokesperson for today is. And then let's go to the practice quiz for today. So problem number 1. Gives the height of an object and find the average velocity over a time interval and estimate the instantaneous velocity at t equal 1. So I'm going to give you a minute or two for that problem. All right, so let me have you stop. So for A, you might have made a little table like mine for the T and the H value, and then the average velocity is the same as the slope. It's the difference in the y coordinates, and you can see if we subtract the larger one from the smaller one, it is 0.07536 divided by 0.02, and I'm going to punch that out. I got 0.03768. Okay, so it wasn't moving very fast. The average velocity was really, really slow in that time interval between 1 and 1.02. And then part B, estimate the instantaneous velocity at t equal 1. I'll give you a minute for that.
Professor Shankin, I think the calculation for, I don't know, I'm getting something different when I did your original calculation. The difference.
Oh, yes, yes.
I was going to say the same thing.
2 instead of 0.02, didn't I? All right, let me
Well, your H, I think, is wrong.
Is the H wrong?
Because I keep redoing that. When T is 1.02, I get 107.47536.
I got the same thing that he did. Maybe you're not plugging in something correctly?
Me too.
1.02. And you're getting 10.
I'm getting 107.
I got 105.47 as well.
You're getting 107. I think it's 105.
Yeah, it is 105, but it's the dividing by 0.02 that was the wrong.
And then the decimal place should be moved over to here. It should be 7 point. So 2 places over.
I actually got 3.768.
Yeah, it's the 3. It's the 3.
I got the same thing.
Yeah, so did I.
All right,
3.
let me do that division again then. So 0.07536.
Oh, I see what I did.
All right. So then this is not correct. It should be 3.768. All right. Everybody in agreement with that now? For A? All right.
Yes.
Okay. Now
Yes.
let's go to part B. Estimate the instantaneous velocity at t equal 1. And I'll give you a little time to think that over. Suppose this is all the information that we have. this right here. All right, let me have you stop. If this is all the information that we have, our best guess for the instantaneous velocity at t equal 1 would be this number, 3.768. Because we want a very small time interval, really close to it, to get the average velocity. Now, this though isn't as good as we would like, because we really want a smaller interval. Suppose it was 1.001. Okay, then this will give us two things. It'll give us a better estimate with a smaller interval, and it will tell us, since we have more than one average velocity, which direction we should be going in. Should I be taking a number a little bit bigger than this, or taking a number a little bit smaller than this? The instantaneous is looking at a bunch of numbers in a sequence and kind of saying, you know, which direction is it going into? All right, so our best estimate at first would be this. Let's do it again now with 1.001, and I'm going to punch that into my calculator. You can be doing the same thing. And then we can verify so we don't get all different answers again. All right, so I get 105.4038. So then, when I take, now I'm going to do the average velocity between these two. So my new slope is going to be the difference in the y coordinates, and everything's going to cancel out except for this. I'm going to have 0.0. Another 0, 3, 8, divided by, and then 1.001 minus 1 is 0.001. So that'll just move this decimal place 3 places to the right, and I'll get 3.8 right here. And then I can get a better estimate for the instantaneous velocity at t equal 1 by saying, hey, these should be getting larger as a sequence. So my better estimate might be, maybe it's going to be 3.9, or maybe it's going to be even 4 or something, but I can see which direction that we're going to. Now we're eventually going to take some gigantic shortcuts and be able to get this instantaneous velocity incredibly fast, and we would get the actual answer is going to be okay, the precise instantaneous velocity is going to be 3.8, and this should be probably a little bit smaller than this. This was just rounded off to be 3.8. All right. Any questions or comments on this first one?
So the answer for number B, it's 3.8. That should be the answer.
Um, two possible answers. If you were doing it just after we had done A, your best estimate would just be 3.768. And then then I embellished it a little bit. And then I put this. So then my adjusted answer would be 3.8. But yes, if you were just doing it in the order of A and then B, you would have just said 3.768. Okay. So notice, to get the instantaneous velocity, sometimes if all we need is a crude approximation, sometimes all we do is do 2 points that are really close together to get that in. But if we can take more than one interval, we can get a better estimate. All right, let's go to number 2. Y equals x squared, approximate the slope of the tangent line, x equals 3. And let me give you a little bit of time for this. Okay, let me have you stop. And if you felt a little lost on here, then I'm accomplishing my objective. I'm taking away a little bit of the structure and seeing how you can do. And it may be that you need some more of that structure for a little while. Let me, but I'm trying to get at the heart of the issue and see if you can construct these things yourselves. So first of all, this is a parabola. And when x is 3, you're at a height of 9. And your instantaneous slope is something pretty steep up here. And to make a table of values, to get this, you need 3 and then something right close to 3. Maybe 3.01. And then if you took something even closer to 3, we might get even more. But this might be enough to get us a reasonable guess. All right, when I plug in 3, I get 9. 3.01 squared, I get 9.0601. And then the slope is the difference in the y-coordinates over the difference in the x-coordinates. Move the decimal place 2 places to the right. we're going to get something like this. And by the way, if we'd used 3.001, we'd have gotten 6.00 something. And the instantaneous slope at 3 turns out to be exactly 6, but we wind up getting something really close to it when we pick 2 points, 3 and then a point just a little bit away from it. Now, it's not true that you always have to pick your second point larger than it. We're kind of favoring to the right, which is kind of natural for us. But it would have been just as valid to pick 3 and then the second point is 2.99. I mean, either side of it is just as important. All right, so before I go on from this one, I need some feedback on this. Let me know if you could get this on your own on number 2. Or where you're at in this kind of like, oh, you know, I need a little bit more help yet to be able to get this completely on my own. All right. Let's go to number 3. Find this particular limit by making a table and making a graph. All right, to make this table, I'm going to be picking numbers right close to 2, like 1.9. But when I do that, I get negative 0.1 over negative 0.1. It turned out to be 1. And no matter what I pick, whether it's below or above, like 2.001, I'm going to always get the same number over itself, and I always get 1. So this limit appears to be 1 when we do a table. If we do a graph, you graph this. And when I graph something like this, suppose I go into Wolfram Alpha, type y equals x minus 2 divided by x minus 2. It just shows me a line at 1. Now it does have a hole right above 2. There's a hole in it. It won't be able to show us that. Alright, so on the graph, we get the same thing. At 1, at a height of 1, we wind up getting this line right here. And so as x approaches 2, here's 1, here's 2, as x squeezes in on 2, this stays at a height of 1. So again, it reinforces that we get 1. And normally, you want to find the limit by just plugging it in. But if you plugged in 2 into this function here, you get 0 over 0, and it doesn't tell you. So we needed some alternate technique, and when everything else fails, we can always revert to a graph, a table, and a graph. Okay. All right. Any questions on number 3? All right. If we're good with that, let's go to number 4 now. Newton needed the idea of limits to find what? And for this, I want you to get into your discussion groups and come up with the best answer you can. It'll be a short sentence. And then I'm going to poll a couple different groups, and then we'll put in a formal answer for this. But check in with each other for this. So 30 seconds more. All right, let me go to group 4. Oh, and by the way, group leaders, if I call on a group and there's somebody designated as a leader but they're not responding, maybe they've stepped away from their computer for a minute or something like that, then it'll fall back on the group leader then to answer the question. So group 4, what's your answer?
It has to do with motion, the limits.
It had to do with motion. Motion of what?
I'm not too sure, but most of the problems we've been doing are like dealing with velocity and stuff. So basically, just like I'm just thinking like maybe like I don't know. I'm just thinking like just basic velocity of like anything right now.
All right, you're right on track. Is this Sally?
Yep.
Okay. So it was motion, and can anybody add a little bit more clarity to that? I'll open this up to anybody else.
It has to do with the velocity of the planets at any given time, so instantaneous velocity.
Very good. It was why the planets were moving in the path that they were moving around the sun, and he needed to get an instantaneous, like an instantaneous velocity. And so if we generalize that for our purposes, Newton needed to find the instantaneous slopes. So let's just put that here as our answer. And instantaneous slopes. That's why he needed that. And you can't get the instantaneous slope. You can only get a bunch of different slopes at smaller and smaller intervals. But if you take a few of them and look at the pattern, you can then kind of start to derive what an instantaneous slope is. All right, now you need limits to get this. And we're going to be going into limits more in detail today and how we evaluate some very difficult limits. And that's going to be 2.3. But before 2.3, are there questions on homework? I think there was 2.2 that the spot check was due today. Any questions? 2.2.
Yes, I have a question.
Yes.
I was trying to figure out. Open my notes. 36.
Say it again.
36.
36. Okay. All right. So let me go here. This is on page 70. And so we got to find this limit, and the first thing we would do is we would plug in 0 for h. But as soon as you do that, you wind up getting some strange things. Plug in 0 for the h, you would get 1 to the 1 over 0 power. Now that's a strange thing. And then you'd get times 2e squared. The 1 raised to the 1 over 0 power, well, 1 divided by 0 does not exist. And then
Shouldn't it be 2? It's a 1 plus 2h. So are we
but the
doing
h
the
is
first
0.
part?
When h is 0, 2 times 0 will be 0.
Oh, that's right. Okay.
Okay, so what's in the parentheses will just resolve down to 1, but then it'll be to the 1 over 0 power. Now, this thing will be slightly bigger than 0, the 2h, while this is going off to infinity. And this whole expression in the top, it's something that we can't compute. And so when you get something, when you plug in 0 and you get something that, like undefined, 1 divided by 0, we have to take a different route. So we're going to have to make a table of values for this. So we'll just make a table. And then we're going to put that huge expression over here. And then what are we going to pick? We cannot put 0 here, but we're going to pick numbers very close to 0. 0.1, 0.0.
Yes, thank you.
Yes? Was that somebody asking a question? Or was that just a mic that was accidentally open?
It's just, I think it looks like Amanda's mic is still on.
Thanks, Kylie. So we gotta just put this into either a graphing calculator or into a like Wolfram Alpha, and then evaluate it at these particular points. And so in my graphing calculator, I would just plug it in, and let me put it into my graphing calculator real quick, if I can. 1 plus 2x.
Lady.
Alright, I think I'm putting it into my graphing calculator correctly, and I'm going to graph it. No, I made an error. Alright, this is a complex expression. You just kind of put these different values in and then see what it turns out in here. And
For point 1, I got 0.3791. I don't know.
Thank you. Did you get any of the other values, or anybody else have these?
Yeah, I have, for 0.01, it was 0.48535.
Okay.
And then for 0.001, it was 0.4985.
And it looks like, as this is going towards 0, this might well be going to 0.5. Okay. And then we could also graph the expression, and in the graph we might see the same thing. The graph might look, as we get, if here's 1, as we get closer and closer to 0, this thing might be getting closer and closer to 0.5. Something like this. Okay. Thank you. Any other questions?
I just have a question about the same one.
Yes.
So I did all that. I was just wondering if I had to do it for the negative as well, since it's in close to 0. I was always getting an error if I use the negative.
If you use a negative, you're getting an error. Good point. I wonder why it's giving you an error. 1.1 It seems like it should work even with negatives. I don't see any particular problems there. So I don't know why you're getting an error with the negatives.
Oh, okay, that was just me then.
Okay. Yeah, there's nothing intrinsic about this that should give it a problem with negatives. And actually that would be more complete if we did check the negative values as well. Okay, any other questions?
Could you go over number 24, I think?
20,
Oh, no. Let me see. Not 24, I'm sorry. 29.
29. Okay. Let's go So it's similar, estimate the limits numerically and graphically. And, well, actually, let's just look at it here. When a is equal to 1, the first thing we try to do is just plug 1 in. But notice that I would get 0 in my denominator. If I plug it in to the numerator, I'll wind up getting cosine of 0, which is 1. And I'll get 1 minus 1. I get numerator being 0 and denominator being 0. So this one, by plugging it in, it doesn't give you any extra information. You just get nonsense, 0 divided by 0. So the only way we can do this is estimate the limit graphically and numerically. So again, I would just make a table of values, and then when I make my table, I would plug in values close to 1, like 0.9, 0.999, 0.9, or I could do 1.1, 1.01, 1.001. Numbers that are getting closer and closer to 1, and then see what this gives me. And then I can also just look at the graph of that function and to see what happens to the heights when x is getting really close to 1. So there's nothing different about this one than the previous one. They're both just really complex functions that are, you just got to make either a table or a graph from. Okay, I think that's all I can say for that one, Kylie.
Okay, thanks.
You're welcome. Anything else?
What about 41? I know I did it right, but I know there's a faster way to do Lano.
What number again?
41.
41. Okay, when you substitute 0 for h, you get 0 in the bottom. So that's a problem. And when you substitute 0 for h up in the top, you're going to get ln of 1, which is asking the question e to what power is 1, which is also 0. So you're going to get 0 over 0. This one doesn't work. So again, this is the same thing. The only way we can do these really tough ones at this point, we're going to learn other techniques starting today, but at this point, the only way we could do it is by making a graph or a table. And at least it's a shorter function, less to punch into a calculator. But you plug in numbers like 0.1, 0.01, 0.001, and then see what happens with these values. So again, it's going to be the same thing, and really there is no shortcut to that. Just plugging those in or sticking it into a graphing calculator. And who was it that asked that question? What's your name?
Gerardo.
Gerardo. Okay, thank you, Gerardo. And any other questions? We're going to get out of that area of asking you to do it with graphs or tables because we're going to come up with a better technique starting today. But the beginning of it is making you realize how you kind of need a graph or a table and how they could be helpful. All right, if no other questions, then let's go to the new section. 2.3, techniques for computing limits. And I'm going to do it on the whiteboard. And so let me set up my whiteboard here. So 2.3 techniques for computing limits. And we're going to go to some of the limit laws. So number 1. And this is going to be part of the training you get in this course to look at the laws of something new. Whenever we come up with something new, and now the new idea that we have here is limits. And we're going to be always, whenever we come up with something new, looking at what are the properties of this new thing that I'm looking at. And so we're going to go here and here are the limit laws. And the first one says, well, let me look at this whole thing. It's assumed that the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. The following properties hold where c is a real number and n greater than 0 is an integer. And the first one is talking about the sum law, the limit of a sum is equal to the sum of the limits. And what this is meaning is, let me shift over to the camera view. The first limit law, the limit x approaches a and an example of this would look like this. Suppose I was taking the limit as x approaches 1 of 5x squared plus 7e to the x. Well, what this limit law says that I can do is look at the correspondence. This would be my f of x. This is another function of x acting like the g of x. Notice I've written the limit one time. Now, it says that this is equivalent to two separate limits. In other words, the limit law distributes, and we can wind up distributing it in to both parts, and it distributes in such a way that is incredibly easy and natural. And now if I was to continue with this, I could then say, this limit, I could just plug in 1 into here and I'm going to get 5. And here I'm going to substitute 1 into here and I'm going to get 7e. And then I would say, that's my answer. Alright. Now this might seem like, well, isn't this kind of obvious? Isn't this clear and easy? Well, not all laws get to distribute like this. For instance, there are some that we've seen, like multiplying. Does this get to go into both? Yes. This distributed into both. But there are some other properties where if you distribute it into both, you are wrong. Like this one. A lot of my algebra students try to do this and tell me that this is x squared plus 9. But they are wrong. This one doesn't distribute into both of these things. You have to do this by foiling it out. X plus 3, and then you're going to get a middle term plus 6x, and so on. Not all things work where they distribute out like this. In general, functions usually do not. It's usually not the case that they distribute like this. Typically, no. Like the cosine function, the sine function, sine of a plus b is not the sine of a plus the sine of b, and so on. Most functions do not work like that. Some really simple linear functions can work and distribute like that, but most do not. But what it's saying is the limits follow very straightforward, easy to remember properties. The limit of a sum is equal to the sum of the limits. So it's a property that seems really simple, but is actually quite powerful for us and tells us something very important about limits in general. All right, I'm going to take a quick screenshot. And paste this. And then erase this. Now in words, we like to say that this limit law is like this. This is the limit of a sum, because here's the sum, you're taking the limit of a sum, is equal to, now these are two separate limits. This is the sum of the limits. The limit of a sum is equal to the sum of the limits is telling you can distribute the limits like this. All right. Now similarly, we see this with subtraction. So number 2, the difference, the limit of a difference is equal to the difference of the limits. And there's not an easier way that the limits could have worked. It just distributes right along. And number 3, the limit of a constant times a function is equal to a constant times the limit of a function. It just gets to pull right out. So that one, number 3, could look something like this. The limit as x approaches 5 of 7x squared is the same as 7 times the limit as x approaches 5 of x squared. Now this is 25, and then 7 quarters is $1.75. Something like that. Now we're going to come up with lots of different properties throughout the semester, lots of different new things, and each one of them we're going to look at what are their laws. It's a new concept. All right, now products work the same way. The limit of a product, you get to distribute product to two limits. Quotient, same thing. And of course it says you cannot divide by 0. And exponents, it works the same way, that the exponent can happen later. The limit of a function to a power, you can take the limit of the function and then get that limit and then later raise it to a power. So you can delay when that happens. And the same thing with roots, delaying when it can happen. All right, any questions on these limit laws? All right, so it is about 12:30, so this is time for a 15-minute break. Let's start again at 12:30, no, 12:44. 12:44, we'll start again.
Professor, it's Francis.
Yes.
Hello.
Yes, Francis.
I will have to leave early, like at 1:30 today, because I have to take my daughters to a dental appointment at 2.
Okay, no problem.
Okay, thank you.
Thanks for letting me know.
Thank you.
Okay. we're on a break, so I'm muted, so you're okay.
That's sweet. You know, it was really great because I got to spend time with you. You know, we spent 26 hours driving up there, 26 hours driving back. When we were there, we saw Grandma and we went up to the cottage and we saw almost all the family. Not, you know, either at the cottage or they came to see Grandma. One of Bob's nieces has a 3-year-old son and a 6-month-old, and I hadn't met them.
All right, let's get started again. And now that we have the properties, the properties of limits are right here. So if those are the limit laws, then if we look at this problem, and this is a couple of these problems are part of your homework, and 7 through 13, it says assume we don't know what the function f is, but as x approaches 1, the limit as x approaches 1 of f of x is 8. And what that means visually is, let me just send you over here, the limit what it means is I have no idea what my function f is. But when x is getting close to 1, the height is getting really close to 8. It's going really through this point somehow. And I don't know how it goes through. It might be falling, it might be rising, it might be, who knows. But it's going through this right here. Now it could even be like this, because remember the limit doesn't care what happens at that point itself. But as we get really close to 1, this function gets really close to 8. Now on g, as x gets really close to 1, it gets close to 3, and h, as x goes close to 1, h gets close to a height of 2. Compute the following limits and state the limit laws used to justify your computations. Now, there's a couple of these problems, but they're important problems. It has to do with learning how to see this new idea in terms of the laws that govern it. And what I want you to do on these problems is right above the equal sign, you need to state the property number that you're using to go through the equal sign. So we're going to do this modification of number 11. I put an extra number in there, 3. And so if I'm going to use one of these properties, which one of those properties would I use first? So just looking at these properties, there's a sum property. Let's come back to here. Well, no, I wouldn't use the sum, but maybe the difference property. Then there's also the property of a constant times something. That's in there as well. Constant times something. And which one of these properties do I wind up using first? So I'm going to ask you to discuss that briefly in your groups, and then I'm going to call on a group. Which property first? And it might seem like it doesn't matter, but it really does. One of them is correct, the others are not. Which property do I use first? All right, let me ask group 6. Which property do I use first?
We would say that the constant property would be the one that you use first.
Constant times a function. All right, now let me explain. If I did the constant times the function first, then I am going to have to ignore all of this. And I'm going to have to pretend like that doesn't exist for a while. And that is not allowed. So let me remove that. I have to use a property. Now what is allowed is I can think of all of this as one thing and think of all of this as another thing. And that's just like putting parentheses around the whole numerator, putting parentheses around the whole denominator. That's always allowed. And if I do that, then I can use the division property. Let's come over to here. Which property is that with the division? It's number 5, the quotient. The limit of a quotient is the quotient of the limits, 2 separate limits. That's the one, the only one. So this is property 5. Notice above the equal sign, I'm putting property 5. The number of the property that allows me to do this. And what I'm going to get then is the limit as x approaches 1 of the numerator function divided by the limit as x approaches 1 of the denominator. Now, did I have to ignore something for this to work? No, I didn't. I got the entire thing. That's what you have to be able to do each time. And so you're not ignoring anything. So it had to be the division property first. And it breaks it up into 2 separate limits. And then, now, you might also be asking, why can't I just substitute 8 for that f of x right there, and 3 for that g? And if you do all that, you will get the right answer. But what we're emphasizing in these problems is the use of all of the properties of any new tool that we have. This new tool is limit, and we want to really be clear about how you use the limit properties. All right. Next, I would then say I could do what was just proposed and use the constant times a function, because I don't have to ignore anything. I could use that on the numerator, and then on the denominator I could also do that at the same time, and that's the difference. And so this is, if we look at these properties, the constant is property 3 and the difference is property 2. So I'm going to say I'm going to use 2 and 3. Properties 2 and 3 to make 2 separate limits on the top. No. On the top, the 3 just comes out in front. On the bottom, you get 2 separate limits. And then once you have all these things, then it's simply a matter of no property number is needed anymore. The limit as x approaches 1 of f of x was given to be 8. So this is 3 times 8. The limit for the g of x was 3, for the h of x was 2. So this is 3 minus 2. It's 24 over 1, which is 24. All right. There's all subtleties involved. It was an answer that would have been easy to get to the answer of 24. Because notice if we just substitute 8 right here, 3 times 8 is 24. Substitute 3 minus 2 right at the beginning, we get the 1. We're going to get that answer. But if it's not done this way, you're not going to get credit for it. You've got to show the properties. Any questions here? This subtle use of you can't ignore one part of the problem. You have to treat the entirety of it is something that will be a constant theme throughout calculus. So it's good to get used to that now. Make sure you understand that.
Shankin, I understand everything except just why is the 3 in front of the 5 of the fx?
Oh, I just inserted that into the problem to make it more complicated, so it had more to do with it. Okay, so that was my addition of the problem. Yeah.
Okay.
All right.
So when we're doing the homework, you want us to actually put the property number, or do you want us to just do it
I want
like
you
the
to
way
put
you
the
did it?
property number right above the equal signs, just
Okay.
like I did. Okay. I think the only two that you have to do in the homework with these are 11 and 12, and we did, you know, number 11, a more complicated version of 11. Okay, but I want you to do showing those steps. All right, and let's go then to other stuff. And let's do a number of limit problems. Finding limits. And I'm just going to start with a renumbering with number 1. Number 1, the limit as x approaches 3, 6 over x minus 1. So, the first thing we learn with limits is when we're finding a limit, is all we simply do is substitute this number in. Every time you see x, replace it with 3 and figure out what your answer is. All right. But what we're going to do is we'll always state what the form is before we do anything else. Now, the form on this one is we're going to get a non-zero number in the top and a non-zero number on the bottom. We're going to call that a over a, where it's just some number divided by some number, but neither of them is 0. Okay. And so when that's the case, we just substitute it in, and we get 6 over 3 minus 1, 6 over 2, which is 3. And that's my answer. All right. But these kind of problems are what we call boring problems, and we're not interested in them. We won't be finding limits where the form is a over a, because they're too easy and the answer is obvious and they're not useful. The problems that we'll be finding will have a complication in them. Let's take this one. The limit as x approaches 2 of x minus 2 over 6x. All right. Before I do this one, I'm going to write what form it is. When I substitute 2 in for the x, what I'm going to get is 0 on the top and a non-zero number on the bottom. So we call its form 0 over a. Now, is it okay to have 0 in the numerator of a fraction? Yes. 0 on the bottom is the problem. So if this is the case, you can just substitute it and you get 0 over 12, which is 0, and that's my answer. Number 3, let's take the limit as x approaches 0 of 5 over x. Before I do this problem, I state the form. This is a non-zero number divided by 0. When I substitute it in, I'm going to get something over 0. Is this a problem? Yes, it's a problem. You cannot divide by 0. And as x gets smaller and smaller going towards 0, this fraction will get larger and larger. When x is 1/1000th, you'll get 5,000 as your answer. This does not exist. So, when the form is a over a, the answer you just substitute it in, you're done. When the form is 0 over a, your answer will always be 0. When your form is a over 0, your answer will always be does not exist. All right. Now, all of these are just kind of setting the table. Problems that most of them that you will see will be more like this one. The limit as x approaches 3 of 2x minus 6 over x minus 3. Now, before I do this problem, I state what the form is. So we get in this habit every time we state the form. If you substitute 3, you get 6 minus 6, which is 0. You get 3 minus 3, which is 0. When you get the form 0 over 0, that's the only form that is important to us. That will be the form that most of the problems will be, and it has a name. It's called the indeterminate form. In fact, all the other forms we'll quickly forget about. These are not important because we immediately know the answers. The indeterminate form, though, what it means is you cannot determine the answer from the form. All the other ones, all you do is make the form and then very quickly you got your answer. Here, you cannot determine the answer until you do more work. More work is required. But it does have an answer. Now, we could get to the answer by, if we were using the techniques from the previous section, we would make a table or make a graph and then be able to see what our answer is from either the table or the graph. But this section, we introduce a new way to do it, an algebraic way to look at it. And so what we're going to do even though the form is 0 over 0, the final answer is going to be a very specific number. Let's look. The numerator, what's common between 2x and 6 is a 2. I factor it out. I'm left with x minus 3. On the bottom, I'm going to put parentheses around that. X minus 3. And when I have, just a quick reminder, 8 plus 3 divided by 3 cannot reduce. 8 times 3 divided by 3. Here we can reduce. But here you can't reduce. When it was in this format, 2x minus 6 over x minus 3, as long as there's any kind of a plus sign or minus sign, more than one term, you cannot reduce. Like I could not cancel this 3 with this 6. It would be as bad as trying to cancel this 3 and this 3 over here. The only time that you can reduce is when you have one term, so everything is multiplied together, over one term. Everything is multiplied together. And so we're back over to here. This we couldn't reduce while it was in this format, but while it's in this format I can reduce. It's like this one. So I can divide. I'm going to get the limit as x approaches 3 of 2. Now, as x gets closer and closer to 3, it has no effect on what's in the parentheses. So the limit is still 2. X has been removed from the parentheses. And so my final limit is 2. Now this answer is totally consistent with if I would have made a little table. Because according to our previous section, this is how we would have done one of these problems. We'd have picked a number very close to 3, like 3.01. And when I multiply by 2, I'd get 6.02 minus 6 over 3.01 minus 3, which is 0.02 divided by 0.01, which is 2. No matter what number I'm going to pick, I'm always going to come out with 2 over here. So we're seeing that it's consistent, but we now know a very much more quick and efficient way to get to our limit result, which is just use a little algebraic reduction. And voila, I'll come up with my answer. Now some of the algebraic reductions we're going to look at today get kind of tricky. And it's going to be a real good review of some algebra skills. But in its essence form, it's just reducing algebraically. Now, let me take a little snapshot here. Put it on the screen and copy this over. Come back. And let me see, was there something else before I erase this? I think I remember there was something I was going to point out. Oh yeah. Let me erase all this except this. Alright. When we cross the border and we do this to this, we're taking a little bit of a liberality. 2x minus 3 over x minus 3. What we did is we canceled these out, these x minus 3's out, and we say that it was 2. Now, put in any number you want for x, and this works out. We did it with 3.01, and we found out that it came out to be 2. It doesn't matter what you put. Let's try it one more time. Even a number that's really far away from 3. Let's pick 100. If x is 100, you're going to get 2 times 97 over 97, which is going to be 2. There's going to reduce to 2 every time. But there is one value for x where this won't reduce to 2. And that is if x is equal to 3. Then we get 2 times 0 over 0, which is 0 over 0, which is undefined. You might say, hey, 0 divided by anything should be 0. So shouldn't 0 divided by 0 be 0? But then you could also be saying, hey, shouldn't anything divided by itself always be 1? It can't decide whether it should be 0 or 1. Or this thing is undefined as any fraction with 0 in its denominator. So this thing is undefined. This little step going from here to here, we usually don't make this notation on it, but I'm going to do it one time for our notes. This and this are equal provided x is not 3. If x is 3, then they're not equal. If x is any other number, like 100 or 3.01, then this is true. This reduces to this. The reason why we don't have to make this notation, though, is that we're talking about a limit. It's the limit as x is approaching 3. And one of the aspects about limits is you're not able to get to your destination. We're not allowed to substitute 3 in for x like when we make a table of values. So it's what happens as we get infinitely close to 3, but we're not allowed to get to 3. And so that this and this are not equal to each other when x is 3 doesn't matter, because this is a limit problem. Everybody clear on that? Any questions? All right, let me take print screen. All right, let's come back. What number was I at? Number 1, 2...
That was number 4.
That was number 4, so we're on number 5. Okay. Let's do the limit as x approaches 4 of x squared minus 16 over x minus 4. Now, the first step on any of these problems is we write the form. The form is, if you substitute 4 in, what do you get? 16 minus 16, which is 0, over 4 minus 4, which is 0. That's the only form where we can't immediately state what the answer is. If it was any other form, bam, we're done. We know what the answer is. But since it's this form, we have to keep going. So let me give you a minute and work this out on your own. Figure out what this limit is. So this is the limit. As x approaches 4, I factor out the top. 1 plus, 1 minus. The two middle terms will cancel each other out. And then the 4's could not cancel, the x's could not cancel. But once we've factored, now we can cancel. This is the same as the limit as x approaches 4 of x plus 4. And finally, we substitute it in and we get 8. That's my answer. Now, when you get an answer like this, you might be suspicious and say, "Well, that was a crazy bunch of algebra. I'm not sure I really believe that this is true." Well, one thing we could do to check our work is either graph this function or make a quick little table. And what number do I pick? Pick a number really close to 4. And then I should be getting something really close to 8. Let's plug it in and see what happens. 4.001 squared minus 16. I wind up getting 0.008001 divided by 0.001 when I take this number minus 4. And that moves the decimal 3 places to the right. And notice I am getting something really close to 8 when this is getting really close to 4. But I'm getting these answers with this algebraic technique. Whereas the previous section, that was the only tool I had. Now I have a better tool using algebraic reduction and cancellation. Okay, do this one. So I want you to do this one and then check with your group real quick. And then I'll call on a group, see what the answer is. All right, 30 seconds more. All right, group 2, what do you have?
The limit does not exist.
Limit does not exist. Okay. And how did you start it, group 2? What was the first thing you did?
So we inputted the 3 where the x is, and then we got 9 at the top, at the numerator, 9 minus 16, negative 7, and then at the bottom 0, so it's the form of a over 0.
Very good.
So yeah.
If you just do your form first, then you're all set. And as x gets closer and closer to 3, this thing gets closer and closer to 0, makes the fraction super huge, does not exist. Check. Now, some of the factoring ones are simple, kind of like this. Some involve more algebraic steps and get kind of complex, as in this next one. Find the limit as x approaches 4. One over x minus 1 over 4 divided by x minus 4. So, let me give you a minute to work on this on your own. And by the way, that was Alondra on the last one. Is that correct? That was speaking last?
Yes.
Okay, great. All right, so on this one, what's the form? When I substitute 4 in, the denominator is 0. When I substitute the 4 in up here, 1/4 minus 1/4, I'm getting 0. So the form is 0 over 0. So this means I cannot get my answer until I do more work. I need some algebraic manipulations to help me out. Can I kind of like cancel this x and this x out, or these 4s and these 4s, or what kind of algebraic manipulation might I be able to do?
You can find, for the numerator, you can convert that into 4 minus x over 4x.
Ah, so what you did is you combined these top two with a common denominator, right?
Yes.
Okay, so these top two are going to be the least common denominator is just multiply them together, 4x. So multiply the top and bottom by 4 for the first fraction, multiply the top and bottom by x for the second fraction. Now they're both going to have the same denominator of 4x. So this is going to be the limit as x approaches 4 of this. They both have 4x, so we can write that denominator just once. And it's going to be 4 minus x over, and then x minus 4. I'm going to turn this into a fraction as well. Alright, so what comes next after this? We have a fraction divided by a fraction. We do that as we call it copy dot flip. Just like if I had 8 divided by 3 divided by 2 divided by 5, it would be 8/3 times in the reciprocal. 5 seconds, like this. Okay? So we're going to do the same thing over here. Limit as x approaches 4 of 4 minus x over 4x times, and we reciprocate the bottom one, copy dot flip, 1 over x minus 4. Any questions here? Everybody okay with this? All right. Now I need a suggestion. What can I do from here? I might check the form now. Maybe the form has changed. Then I'm okay. But if I check the form, I'm going to get 0, over 0 times 1 over 0, which is still 0 over 0. The form is still indeterminate, cannot figure out my answer. Anybody have an idea what to do next?
Factor out a -1 from the x minus 4 term on the bottom to turn it into 4 minus x.
That is correct. Now we can do that, factoring out a -1, we can do that either on the 4 minus x or on the x minus 4. Okay. I'm going to choose to do it on this one. I'm going to factor out -1. Alright. And I'm about to erase stuff, so let me do a quick print screen. Copy it in. Alright, so let me review factoring out a -1. It may have been a while before you did something like this, but suppose you were told to factor -x squared minus 3x minus 2. You might struggle with this by trying to put -x and x and factoring it out, but actually much quicker is if you factor out a -1. And then instead of doing this route, you do this, and then you've got it. So at any point, if you decide to, you can factor out a -1. You can make the problem more simple. Right, so that's what we're going to do right here. And I'm going to come down here, and this is the limit. X approaches 4. I'm going to take this one and factor out a negative sign, and then the 4 will become negative, so it'll be -4 plus x, but instead of writing it -4 plus x, I can also write it as x minus 4. That's the same as -4 plus x over 4x times 1 over x minus 4. And then we are going to reduce, and this, finally these reduce. Now notice, the thing that I'm reducing is the thing that was causing the 0 over 0. If I plugged in the 4, that would cause a 0, that would cause a 0. But I'm getting that to reduce now, and so that will eliminate my difficulty. The limit as x approaches 4, and I'm going to get inside here -1 over 4x times 1 over 1. And then when I substitute the 4 in there, I'm going to just get -1/16. And that's it. So the final answer is -1/16. Now, if you're a math skeptic, which I tend to be, and it's served me very well over the years, is I would look at something like this and say, that was a whole bunch of mumbo jumbo. I'm not sure that I can really believe this answer. I would have to look at it and kind of check my work. And I would say, let's plug in a number really close to 4. See, that's really, really close to 4. If this was really true, this result should be really close to -1/16. Now, -1/16, I'm going to punch that out in my calculator. is negative 0.0625. So now let's plug in this 4.001 into this. 1 divided by 4.001. Oops. And I get, in my calculator, negative 0.0624843 da, 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 da. And notice that is incredibly close to that right there. And that does check that this math mumbo jumbo actually really is working. Any questions? All right, let me take another snapshot. And let's look at another one. Oh, and I just forgot. Was that number 5? So are we on number 6 now?
No, we're on number 8 now.
We're on number 8. Thank you. All right. And let's see which one in my notes tells me to do. Let's do this one. Find the limit as x approaches 9 of square root of x minus 3 over x minus 9. All right, so my first step is I state the form. Anything but 0 over 0 and I immediately know my answer. But the form is going to be 0 over 0. I get 3 minus 3 over 9 minus 9, 0 over 0. All the problems that are challenging are going to be the 0 over 0 form. What in the world can I do with this so that in an algebraic way I might be able to get to this answer? Now and then you might run into a problem where there's no algebraic way to get it, and then you just make a table of values or make the graph and then say, oh, that's the best I can do. But this one, we can actually get it algebraically if we think in the right manner. Does anybody have an idea? Okay, doesn't surprise me. Nobody has an idea. Because it's something I need to remind you of that might be a little further back in your math background. Do you remember this topic of rationalizing the denominator? Suppose I gave you 3 over the square root of 2. How do I rationalize the denominator? What does rationalize mean? Well, the square root of 2 is what we call an irrational number. As a decimal format, it goes forever without ever getting into a repeating pattern. To rationalize it means to get rid of the square root symbol so that it's... And suppose you were adding two fractions. Like suppose you were adding this plus 1/4. if you're adding these two together, you'd have a pretty nasty common denominator. So one of the things that we often do is get rid of the square root in the denominator. How do you get rid of the square root in the denominator? Let me ask. Go ahead.
You multiply it by square root of 2 over 2.
Very good.
Square root of 2 over the square root of 2.
Square root of 2.
Square root of 2 over the square root. Now,
I'll do this, and I get 3 square root of 2, and then I get square root of 4, but the square root of 4 is just 2, and I have this. Notice, though, you cannot do something like this. That would not work. And the reason why you can't square numerator and denominator is because you change the values. Like for instance, if you had 1/2 and you wind up squaring, because this is really 1/4. When you square numerators and denominators, it changes the value of the fraction. When you multiply top and bottom by the same thing, it keeps the fraction value the same, it just changes its format, so it looks different. All right. Now, if we had something like this, how would I rationalize this denominator? One approach might be like this. You might try this again. But this fails to work, because you'd have to distribute this into both. And although you would get a regular 2 here, you'd still get this right here, and that's a problem. You didn't get rid of the square roots in the denominator. All right, so another approach might be multiplying top and bottom by exactly what's in the denominator. And if we use that approach, it also doesn't work. The reason why it doesn't work is you have to FOIL out everything in the denominator. And when you FOIL out, your middle terms will still contain square roots. The approach that does work, though, is this one. It's called multiplying by the conjugate. What we do is we multiply by square root of 2, same two terms, but whatever the sign is, we change it. Now, when we multiply by the conjugate, what happens is the top goes like that, but the bottom, the middle two terms will cancel each other out. And that gets rid of the square root in the denominator. And that actually rationalizes the denominator. All right, so that's the technique that we're going to use up here. So I come up here and I say, all right, I'm going to multiply this. Even though it's not the denominator, even though it's in the numerator, I'm still going to use this same technique. Oops, square root of x plus 3. Same two terms, but change the sign in between. Whatever I multiply on the top, I have to do that same thing on the bottom. And then watch what happens. I'm going to get the limit as x approaches 9. Now, the numerator, I'm going to multiply out. When I take this times this, I get x. This times this, I get plus 3 square root of x. This times this is minus, what's x? Minus 3 square root of x. Notice those two middle terms are going to cancel out. Minus 9. These two kill each other off. And the bottom, I'm going to leave, I'm not going to FOIL out. Okay. So what this is going to do, this is going to give me the limit as x approaches 9 of x minus 9 over x minus 9 square root of x plus 3. All right, I'm going to put, notice at this point, if I substituted my x as 9, I would get 0 over 0. But as soon as I reduce, it's no longer going to be the form 0 over 0. This is going to equal the limit as x approaches 9, 1 over square root of x plus 3. And when I substitute, finally I can substitute in, because it's now a over a, and I'm going to get 3 plus 3, I'm going to get 1/6. That is my limit, and I found it algebraically. But I used this kind of thinking that I learned over here. And let me clean this up a little bit and take a snapshot of this. And that takes us to the end of our time today. And your homework is 2.3. Back into the normal spot check routine. I'll be spot checking 2.3 tomorrow. Any questions or comments? And for the first time, almost ever, I am remembering to stop the video. I'm going to go and stop it right now.